just imagine what you'd see if you had a lens the size of a galaxy. Well, believe it or not, galaxies themselves can actually act as lenses.
Astronomers all over the world have been sent scratching their heads as the James Webb Space Telescope detects 6 new galaxies that should not exist. With the telescope, astronomers and scientists can literally go back in time and see how galaxies were formed over billions of years. But no one was prepared for what they saw recently. 6 previously undiscovered galaxies that threaten to destroy established cosmological theories and ideas. Scientists have declared that these discoveries are, technically, not supposed to exist, thus defying established laws of science. What are these new galaxies? How did the James Webb Space Telescope find them? And what are the implications of these discoveries? Join us in this video as we show how the James Webb Telescope detected a structure that should not exist. The study of the universe on its grandest scales, which is the realm of cosmology, is an exciting and ever-expanding field of inquiry. As our technology advances, so does our ability to probe the depths of space, revealing new and awe-inspiring wonders. At the forefront of this cosmic exploration stands the James Webb Space Telescope, named after the astronomer James E. Webb, and is the largest and most powerful space telescope ever built. Its primary mirror, a gigantic structure measuring 6.5 meters in diameter, comprises 18 hexagonal segments that unfold like an origami flower. This immense mirror, combined with its advanced infrared sensors, allows the James Webb Space Telescope to look back in time to the very beginnings of the universe. It captures light from the first galaxies that emerged just 250 million years after the Big Bang. The James Webb Space Telescope's mission seeks to transform our understanding of the universe. It aims to unravel the mysteries of the universe's formation, shedding light on the birth of stars and galaxies, the evolution of cosmic structures, and the presence of potentially habitable exoplanets. By observing distant objects that emit light in the infrared spectrum, the James Webb Space Telescope can penetrate dust clouds that obscure visible light, revealing hidden depths of the cosmos. The discovery of new galaxies holds immense significance in the realm of cosmology. Each newfound galaxy represents a piece of the cosmic puzzle, providing clues about the universe's composition and evolution. By studying these distant galaxies, astronomers can gain insights into the formation of stars and planets, the distribution of dark matter and dark energy, and the overall structure of the universe. The James Webb Space Telescope's ability to detect faint, distant galaxies has already yielded groundbreaking discoveries. In July 2022, the telescope captured images of galaxies that existed just 620 million years after the Big Bang, the farthest galaxies ever observed. These observations push our understanding of the early universe to new frontiers, revealing the first galaxies that emerged from the primordial chaos. But what makes this telescope special and amazing? The James Webb Space Telescope is the largest and most powerful space telescope ever built. It is an infrared telescope, meaning that it is designed to detect light in the infrared portion of the electromagnetic spectrum. The James Webb Space Telescope's primary mirror is 6.5 meters in diameter, 3 times larger than the Hubble Space Telescope's mirror. This means the JWST can collect 4 times as much light as Hubble, allowing it to see fainter and more distant objects. The James Webb Space Telescope is also much colder than Hubble. This colder temperature allows its infrared detectors to operate more efficiently, making them more sensitive to faint infrared light. Hubble operates at about -123 degrees Celsius, while the James Webb Space Telescope operates at -218 degrees Celsius. The James Webb Space Telescope also has 4 scientific instruments, each of which is designed to study a different aspect of the universe. These instruments include 1. The near-infrared camera. The near-infrared camera is its flagship instrument. It is designed to take images of the universe in the near-infrared spectrum, which is the portion of the infrared spectrum that is closest to visible light. This camera will be used to study a wide variety of objects, including stars and planets, galaxies, and nebulae. 2. The near-infrared spectrometer. The near-infrared spectrometer is a spectrograph that will be used to study the spectra of objects in the near-infrared spectrum. This will allow astronomers to measure the chemical composition of objects and to study their motions. 3. The mid-infrared instrument. The mid-infrared instrument is designed to take images of the universe in the mid-infrared spectrum. This is the portion of the infrared spectrum that is farthest from visible light. This instrument will be used to study specific objects, such as dust clouds and stars in the early stages of formation. 4. The fine guidance sensor and near-infrared imager and slitless spectrograph. The fine guidance sensor and near-infrared imager and slitless spectrograph are a combination of two instruments. The fine guidance sensor will be used to keep the James Webb Space Telescope pointed accurately at its targets, while the slitless spectrograph will be used to take images and spectra of objects in the near-infrared spectrum. The James Webb Space Telescope is also a significant upgrade over the Hubble Space Telescope, allowing it to study a different part of the electromagnetic spectrum than Hubble. Hubble is an optical telescope, meaning that it is designed to detect light in the visible portion of the electromagnetic spectrum. The James Webb Space Telescope, however, is an infrared telescope, meaning that it is designed to detect light in the infrared portion of the electromagnetic spectrum. As part of its mission to look back in time and observe the origin, nature, and formation of galaxies and search for exoplanets, the James Webb Space Telescope has recently discovered 6 new galaxies. These newly discovered galaxies have captivated the attention of astronomers worldwide, offering absurdly improbable glimpses into the earliest days of our universe. These galaxies, described in a new study based on Webb's first data release, are so far away that they appear only as tiny reddish dots to the powerful telescope. By analyzing the light emitted by these galaxies, astronomers established that they were viewing them in our universe's infancy, only 500 to 700 million years after the Big Bang. Such early galaxies are not in themselves surprising. Astronomers expected that the first star clusters sprung up shortly after the universe moved out of the period generally referred to as the Dark Ages. This is about the first 400 million years of its existence, when only a thick fog of hydrogen atoms permeated space. But the galaxies found in James Webb images appeared shockingly big, and their stars were too old. According to experts, the new findings conflict with existing ideas of how the universe looked and evolved in its early years, and don't match earlier observations made by Webb's less powerful predecessor, the Hubble Space Telescope. In the words of Joel Leja, assistant professor of astronomy and astrophysics at Penn State and one of the authors of the study, we had specific expectations for the type of galaxies that live in the early universe. They are young and small. Previous studies of the early universe with Hubble and other instruments tend to find small, blue baby galaxies at early times. Objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. In general, young stars shine bright blue. As they age, these stars develop a redder glow as they burn through their fuel and cool down. But in the ancient galaxies that Webb was built to spot, astronomers had not expected to see old red stars. They also had not expected to find galaxies more massive than perhaps 1 billion suns. But those reddish dots, revealed in Webb's deep fields, appear 50 times more massive than that. The most massive galaxies in our sample are expected to have masses 2 to 4 times lower than that of our own Milky Way. Scientists were thus shocked to find out that some of these galaxy candidates are as massive as our own galaxy when the universe was 3% of its current age. Leja said that before astronomers start rewriting cosmology theories to explain how these galaxies came together so quickly after the Big Bang, they will have to ensure the odd red dots they are looking at are not something else. Most of the alternative explanations, however, also require entirely new concepts. Leja said, for example, stars in the early universe might emit light in exotic ways due to their lack of heavy elements, and perhaps we're not incorporating those in our models. Or alternatively, perhaps our understanding of how stars form locally, for example, how many stars form from gas as a function of the mass of the stars, is totally inapplicable in the early universe. These things would also be exciting to discover and would also overturn our understanding of star formation in the early universe, just in a very different way, he added. The most important thing is that spectra give very precise distances to these objects, said Leja. According to the study, the distance and the identity of these objects is correlated. If we know the distance, we can pin down the identity, and vice versa. So a spectrum will pretty immediately tell us if our hypotheses are correct. These discoveries are as amazing as they come. To have scientists already challenged to rewrite their theories about the early universe, just a little over 6 months after the Webb team released the first observations from the Grand Observatory, is unthinkable. Leja said that while the objects so far do appear to be galaxies, there is a real possibility that some of the entities they found could be supermassive black holes. Black holes are areas in space where a large amount of matter is packed into an area millions of times as massive as the Sun, and where NASA says gravity is so strong that nothing, not even light, can escape. But even if it turns out that some of the 6 objects they found are black holes, it still shows an astounding change, according to experts. Regardless of subsequent reporting, the amount of mass discovered shows that the known mass in stars at this period of our universe is up to 100 times greater than scientists had previously thought. The idea that massive galaxy formation began extremely early in the history of the universe upends what many of astronomers had thought was settled science. According to the study, they have been informally calling these objects universe breakers, and they have been living up to their name so far. In a later statement made at Penn University, Leja said, "We looked into the very early universe for the first time and had no idea what we were going to find. It turns out we found something so unexpected, it actually creates problems for science. It calls the whole picture of early galaxy formation into question." So, what are these galaxies? Found deep in the cosmos field, a region of the sky teeming with galaxies, these newfound celestial bodies have become the wonder of astronomers as they challenge our understanding of galaxy formation and evolution. The first galaxy is a remarkably compact and massive one. Designated GNZ11, it holds the distinction of being the most distant galaxy ever observed. Its light, traveling for over 13 billion years, reached Earth when the universe was just 330 million years old. Despite its early formation, GNZ11 is surprisingly compact, with a size similar to our Milky Way galaxy. However, in a shocking and puzzling turnaround, its mass is 89 times greater than that of the Milky Way, belittling everything we know about galaxy formation. The second galaxy is named GNZ10 and is located approximately 13 billion light-years away. It exhibits a level of brightness that is beyond what astronomers expected to see, outshining theoretical predictions by nearly 100 times. This has caused astronomers to suggest that it may house a population of stars forming at an accelerated rate. This phenomenon could rewrite our understanding of the early universe's star formation processes. The third galaxy, GNZ9, is situated about 13 billion light-years from Earth, similar to previously discovered ones. It also showcases abundant heavy elements like oxygen, carbon, and nitrogen. These elements, essential for life as we know it, were forged in the hearts of massive stars that exploded as supernovae, enriching the surrounding interstellar medium. The presence of heavy elements in this galaxy suggests that star formation and supernovae were already occurring in the early universe, a crucial step toward the emergence of life. The fourth galaxy, designated GNZ8, located around the same area as the previous one, has a remarkably structured disk, a feature that challenges existing models of galaxy formation. Disks are thought to arise from gravitational interactions within galaxies, but the early universe was too turbulent for such disks to form. This galaxy's existence suggests that disk formation may have occurred earlier than previously thought, potentially altering our understanding of galaxy evolution. The fifth galaxy, GNZ7, is exceptionally rich in dust, a component crucial for planet formation. Dust particles are known to provide the building blocks for rocky planets, and their presence in this galaxy indicates that planetary systems may have begun forming in the early universe. The sixth and final galaxy, GNZ6, is remarkably different from the others as it exhibits a surprising redshift, a measure of how much an object's light is stretched due to the expansion of the universe. This galaxy's redshift is slightly lower than expected for a galaxy at its distance, suggesting that it may be located in a region of the universe with a slightly slower expansion rate. This observation could provide valuable insights into the large-scale structure of the cosmos. The discovery of these 6 galaxies is a testament to the remarkable capabilities of the James Webb Space Telescope. Its powerful infrared capabilities allowed it to peer through dust clouds that obscure visible light, revealing these distant galaxies that have been hidden from our view. Scientists have credited the near-infrared camera for playing a pivotal role in these discoveries. Its high sensitivity and wide field of view enabled it to capture detailed images of these faint, distant galaxies. Additionally, its ability to detect light in the near-infrared spectrum allowed it to penetrate dust clouds, providing a clearer view of these obscured objects. The discovery of these 6 galaxies marks a significant leap forward in our understanding of the early universe. By studying these distant galaxies, astronomers can gain insights into the formation of stars and galaxies, the evolution of cosmic structures, and the presence of potentially habitable exoplanets. Also, this recent discovery has challenged our understanding and theories concerning how galaxies are formed. One of the most significant implications of these discoveries is that they suggest galaxies may have formed much earlier in the universe than previously thought. The James Webb Space Telescope has detected galaxies that existed just 300 million years after the Big Bang, challenging the prevailing view that galaxy formation began around 500 million years after the Big Bang. Secondly, the discovery of galaxies with exceptionally high stellar masses, such as GNZ11, suggests that star formation in the early universe may have proceeded much faster than previously thought. These massive galaxies formed within a few hundred million years after the Big Bang, suggesting that star formation processes were incredibly efficient in the early universe. Thirdly, the observation of galaxies with surprisingly structured disks, such as GNZ8, challenges existing models of galaxy formation. Disks are thought to arise from gravitational interactions within galaxies, but the early universe was too turbulent for such disks to form. GNZ8's existence suggests that disk formation may have occurred earlier than previously thought, potentially altering our understanding of galaxy evolution. Also, the presence of heavy elements like GNZ9 in galaxies indicates that supernovae, explosions of massive stars that forge heavy elements, were occurring earlier than previously imagined. This suggests that the chemical evolution of the universe may have proceeded more rapidly than previously understood, potentially influencing the formation of planets and the possibility of early life. Lastly, discovering these early galaxies has necessitated revisions to existing cosmological models. These models need to account for the earlier formation of galaxies, the accelerated star formation rates, and the presence of heavy elements in the early universe. These observations have pushed us to rethink our existing theories and models, leading to a deeper and more comprehensive understanding of the universe. As new and more powerful telescopes come on board the space exploration drive, we can expect even more groundbreaking discoveries that will continue to shape our cosmological frameworks. However, these recent discoveries of galaxies have far-reaching implications for future space missions and cosmological studies. These discoveries have opened up new avenues of research and highlighted the need for more powerful and sophisticated telescopes to probe the depths of the cosmos. The discovery of galaxies in the early universe provides a unique opportunity to study galaxy formation and evolution in its earliest stages. By observing these distant galaxies, astronomers can gain insights into the initial conditions of the universe, the processes that led to the formation of the first galaxies, and how these galaxies have evolved over billions of years. The James Webb Space Telescope has played a pivotal role in these discoveries, and future space missions are expected to build upon its success. The Vera C. Rubin Observatory, scheduled to begin operations in 2024, will provide a synoptic survey of the sky, allowing astronomers to detect and study a vast number of galaxies, including distant ones like those recently discovered. The discovery of galaxies with high stellar masses and structured disks suggests that dark matter can also play a more complex role in galaxy formation. Additionally, the presence of galaxies in regions with slightly slower expansion rates may provide new insights into the nature of dark energy. With space missions like the Euclid Space Telescope and the Large Synoptic Survey Telescope, astronomers could study dark matter and dark energy in more detail. These missions will provide precise measurements of the distribution of galaxies and the expansion of the universe, helping to refine our understanding of these mysterious components of the cosmos. Also, the discovery of dust in galaxies like GNZ 7 indicates that planetary systems may have begun forming in the early universe. This raises the possibility that habitable exoplanets may exist in these distant galaxies. Finally, the discoveries of these early galaxies have highlighted the interconnectedness of different areas of cosmology. By studying galaxy formation and evolution, we gain insights into the behavior of dark matter and dark energy, the chemical evolution of the universe, and the potential for life beyond Earth. This would require that future cosmological studies strive to unify these different areas, helping to develop a comprehensive understanding of the universe from its earliest moments to its present state. This will require collaboration between astronomers, physicists, and other scientists, leading to a deeper appreciation of the cosmos's grandeur and complexity. With these discoveries, and many more expected to come through in the coming years, scientists and astronomers might find themselves going back to the drawing board and rethinking our generally accepted ideas and theories about the universe and how it works. That actually won't be bad. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.